Good news for students who want to build machines to enter in the robot contest, ROBOCON. Professor Masashi Shimizu of the Tokyo Institute of Technology has made this video to share some simple tips for building a successful machine. Nicknamed Dr.ROBOCON, Professor Shimizu has been chairman of the judges panel for more than a decade and has attended tournaments throughout the world. We're sure that his simple tips will prove useful.
Hi everybody, and this is Professor Shimizu. I'm working for Tokyo Institute of Technology, and for the last 10 years I was in charge of the robot contest in our university. And this video is for the beginners of robot contest. And if you want to join the robot contest, you have to make machines. And the machines for robot contest have many limitations. For example, limitations for weight, limitations for size, and the limitation for energy. So you have to make very light and strong and very low friction machines. In this video, the 5 key points for the robot contest machine will be explained.
Robo Basics. Wheels and bearings are basic elements in a ROBOCON machine and can be designed in many ways. Point number 1, shaft bearings. The first point is the shaft bearing, which is used in many places, like the wheels and arm. Today, we'll look at how they're used with wheels. This is a cross-section of a bearing. Here's the shaft, and here's the bearing. With bearings, it's important to reduce 2 things: the friction force and the torque needed to turn the shaft. As shown here, the friction force is determined by multiplying the force applied to the shaft by the friction coefficient. The torque needed to turn the shaft is found by multiplying the friction force by the shaft radius. To reduce the torque, you must reduce the diameter of the shaft, while being careful to maintain sufficient shaft strength. But how do we reduce friction force? We can either reduce the friction coefficient or the amount of force applied to the shaft. We can cut the friction coefficient using oil or grease. But how do we reduce the amount of force applied to the shaft? This is a bearing. We'll use a wheel as an example. Here's the wheel, the axis, and the bearing. This is an example of bad design. When a wheel is overhung on 2 bearings like this, a very large force is applied to the bearings. This is shown in the equation here. The force applied to the inner bearing, compared to that applied to the wheel, is the same as the ratio of L3 to L2. The force applied to the outer bearing compared to that of the wheel is the same as the ratio of L3 to L1. In this example, the ratio of L2 to L3 is about 2, which means that the force applied to F1 is about twice the amount that's applied to the wheel. The force at F2 is about the same as that applied to the wheel. Adding these together, the force applied to the bearings is 3 times the force that's applied to the wheel. This is the ideal design. The wheel is supported by bearings on both sides. In this design, each bearing receives half the force that is applied to the wheel. Therefore, the 2 bearings together receive the same force as the wheel, which is only a third of the force shown in the previous example. A simple test will demonstrate what a big difference this makes. Let's see how much force is needed to move the machine when the wheels are supported on both sides. This gauge measures the amount of pulling power needed to move the wheeled platform. it begins to roll at about 170 grams. Now, let's see what happens when the back wheels are supported on one side only. They begin to roll at 400 grams. As you can see, single-sided support greatly increases friction, so use double-sided support whenever possible. This test demonstrates how important it is to reduce bearing friction. When building your machine, use this ideal design if you can. If you have to use single-sided support, minimize the distance between the inner bearing and the wheel, and maximize the distance between the bearings.